Summarizing, we started with this equation, which we translated into a matrix equation. We made an assumption that y1, y2, the column vector y1, y2 is e to the lambda t times some column vector x1, x2, leading to this equation, giving us three unknowns and two equations, one for the top row, this times this equals this times this equals this. We have two linear equations in x1 and x2 and lambda, and we're going to try to solve them. Our equation, our matrix equation, is of the form A times an x vector equals a c vector, where A stands for the matrix, x stands for this column vector, and c in this case is the zero vector, and or the zero matrix, the column matrices. I call these column vectors. It's common usage, common reference. A matrix which is in the form of a column is a column matrix. We also call that a column vector, and that goes back to some of the interpretations we put on the vectors in linear algebra. Now, this is a standard part of a pre-calculus course, that we can have a matrix equation to solve a set of linear equations, and the matrix equation is set up like this. And the solution to that matrix equation is just, we multiply the inverse matrix of A times AX, and that equals the inverse matrix times the C vector. And by the associative law, we can pair the inverse matrix with the matrix, which gives us the identity matrix. So we have identity matrix times X equals A inverse C, where I don't really need the parentheses around C. And the identity matrix times X is just X. So that equals A inverse times our C column vector. Now, in the present case, C is the zero vector, so that X would equal A inverse times the zero vector, which would equal the zero vector. This would be very inconvenient because we're trying to find a vector x that satisfies this matrix equation. We don't want a zero vector. That wouldn't give us anything resembling a solution to the differential equation, the system of differential equations. So this won't work. What are we going to do about that? The resolution is A inverse cannot exist, because if A inverse did exist, this equation would hold and X would be the zero vector. And of course, actually that is a solution. That would give us a solution to the equation, but it wouldn't be a very interesting solution. Obviously, if the y1 function is always 0 and the y2 function is always 0, then their derivatives are always 0, so these equations hold, but that's a trivial case. We're not interested in that case. We're interested in the case where we do get non-zero solutions. Well, if A inverse can't exist, then we say, so A is non-invertible. There are a lot of words we use for this. We could call it singular. But the point is that it's non-invertible. And now another result, again, it's a pre-calculus level result, but not everybody had a solid pre-calculus course, and this is a topic which, if you haven't had linear algebra, might well have just been skipped in your mathematics education. A is invertible if and only if the determinant of A is not equal to 0. Now, you should have seen Cramer's rule in your algebra courses. Again, don't want to get on my soapbox about what's being left out of the curriculum, because we're trying to educate our top students with an education that only barely serves our average students. But a standard topic like Cramer's rule often gets left out. A pre-calculus course will typically assume that you know it from Algebra 2 and not cover it, or not cover it very thoroughly. And then if you haven't had a linear algebra course, which is not prerequisite for this course, here you are. And you're going to have to remedy that if that's the case. So our conclusion here is that to get a non-trivial solution, a solution x1, x2 that's not just 0, 0, we're going to have to require the determinant of A to be 0. Now, having done so, we might well be able to find solutions, because if we require the determinant of A to be 0, that's going to restrict our values of lambda. Matter of fact, that's going to determine our values of lambda that will then allow us to solve for x1, x2, because having determined the values of lambda, we have two simultaneous equations in x1 and x2.